Okay, so the third and last speaker for today is Miguel Navascués. He's a researcher here at the University of Vienna. He has done his PhD studies at IQOQI in Barcelona, in Spain. And since 2008 to 2015, he has been a research associate in several different universities, from Imperial College to University of Madrid, University of Bristol, Autonomous University of Barcelona in Spain, Bilkent University in Turkey. And since 2015 until now, he is a junior group leader at the IQOQI, so Institute for Quantum Optics and Quantum Information here in Vienna. And together with this, he has also written a paper titled Theoretical Research Without Project, together with Costantino Budroni, which will also be part of our panel discussion, and proposes basically an alternative idea for funding theoretical research. And now we'll hear more about this.
Thank you, Julia. Yeah, I'm going to present this paper. If you intend to read it, I recommend you not to go to the printed version because the edition is terrible. I recommend you to go to the archive version. Okay, when I was preparing this talk, I collected some amount of tenure and tenure track job ads that I found in Quantiki, quantiki.org. And as you can see, I highlighted that all of them demand the ability from the candidate, the ability to secure external funding. And actually, in one of them, this ability goes before the ability of the candidate to conduct interesting research. It's kind of revealing. I did have to look a lot in order to find these examples. Roughly 1 out of every 2 applications had this kind of requirements. So you see that obtaining funding has become a really, really important asset or requirement or prerequisite in order to get a position in academia. Now, how do you get funding? Well, you want to milk some member state to the European Union, you have to make a grant application. And in the grant application, they will ask you to fill a project. Now, what is a project? It's a document that has two sections. One of them is goals, where you explain what you're going to discover. And the other one, methods, where you explain how you're going to discover it. So, for example, it may be that you want to discover the Higgs boson, so that's your goal. And the method is to build the LHC. Now, this structure is very logical for certain type of experimental sciences. It doesn't really work for theoretical science. It's actually incompatible with the way we conduct, or we have conducted in the past, theoretical science. Why? Well, think of the goals. This is the way that I conduct theoretical science. I set up myself some initial goal, and then I start working towards it. But then after a few months, I decided to change direction in order to achieve a better goal, a goal that I think it's either more accessible or it's even more important than the original goal. And then I'm here, I set myself a different goal, and then I work for some time until I achieve a different goal, right? And this is not the way I do it, this is the way every theoretical researcher works. Now let's go backwards in time, let's say half a year, and then ask this researcher to predict what he's going to do in 6 months from time. The researcher cannot even imagine that he's going to work on this one because he has the initial goal of A. Okay? So that's the problem, right? Theorists do not know, we do not know really what we're going to be working on in the next 6 months, let alone the next 4 years, right? So we cannot really fill this part of a project. How about the second part, the methods? We have to explain how to discover the project. Well, we cannot fill this part either. And I'm going to explain it with some hypothetical examples. Suppose that somebody wants to solve some mathematical problem. Well, there are 2 possibilities. Either you find a method to solve it or you don't find a method to solve it. If you don't find a method to solve it, of course, you cannot fill this section, therefore you don't get funds, and more importantly, you don't get the solution of the problem. But suppose that you find a method to solve it. Well, the thing is that it's theory, right? I mean, the moment you find a method, you find the solution. So you immediately find the solution. Can you fill the methods now? No, because now you have the solution. So the agency would tell you, well, you already have the solution, why are you asking funds for? So in either case, you cannot really fill this section, right? Okay, so you cannot either fill the goal section or the method section. So what can you fill? How do researchers, how do theoretical researchers fill an application? Because we do fill grant applications. Well, in this paper, we claim that we lie, okay? It was criticized, and actually, I think with reason, right? Because actually, you don't have to lie to get funding, right? I mean, so let's examine why we do, and why we don't lie, okay? In order to lie, you have to say something that you know that it's false. Like, for example, this is not a mustache. Okay, this is a stupid lie because it doesn't give me any advantage, right? Normally, we lie for an advantage in order to get something, right? So the image of Machiavelli, right, comes to mind, right? But actually, lying is not what you do when you apply for a project. What you do is bullshitting. So this is different, a subtle difference between lying and bullshitting. When you bullshit, you are saying something that you don't know whether it is true or false, but it doesn't matter. Okay, so it's a theorist applying for a grant, right? The theorist sets some goals and sets some methods to achieve these goals. And of course, it is possible that these methods achieve these goals. These methods end up with a time machine or discovering alien life, right? It is possible. It's just not probable. And it doesn't matter, right? I mean, to the researcher, because once he gets the funds, he's going to do whatever the hell it likes. Now, you could say, well, there are no problems, right? I mean, this is part of salesmanship, but actually there are problems. One problem is that it is dishonest. You're not lying, true, but you're misleading. You're deliberately misleading society when you promise things that you don't believe that you're going to accomplish. It takes a lot of time because it's not like reporting about your own research, right? I mean, I can tell you I can prepare in 1 week perhaps a talk explaining more or less what I'm doing now, right? But bullshitting really requires a lot of imagination, right? I mean, and it's completely sterile, right? Because you cannot publish these kind of things, right? I mean, you have to spend 1 month instead of doing research, doing bullshitting. And then, luckily for us, most funding agencies do not care. Once we propose something, then they're fine. Once they give us the money, we can kind of bend a bit the initial objectives, right? But I've been told that in Singapore, the funding agency is starting to claim money from researchers who do not deliver the goals. And things are getting really, really dangerous. Okay, so in this paper, we proposed a different way to fund theoretical research. It's a grant scheme that works without projects. And the way it works is using a two-step process. First, you have some evaluation of the recent scientific achievements of the candidates. And finally, you distribute the funds. Now, in this evaluation, you have to define some objective function that is measurable that will allow you to quantify the scientific production. And many funding agencies like bibliometric indexes. I think most scientists would prefer some sort of expert evaluation, right? Once you have this objective function, something that you can evaluate, you can measure, you can give it a number, then the problem is how to distribute the funds, not in any way, but in such a way that the future total scientific production, after you make this distribution, is maximized. Now, so we have 2 steps and you have 2 problems, right? I mean, so here you have to define what it is that you want from science. This is not really a scientific problem. What you want from science is something subjective and political, right? So a science doesn't have anything to tell about this subjective function, right? It's something that the agency or the government or society must choose. However, once you choose this function, then computing which is the best distribution is a mathematical problem. This is a scientific problem that we can attack, and this is actually what the paper is about. So in the paper, we start from the premise that you already have decided what it is that you want to boost in science, or what it is that you want from science. And once you know what it is that you want and you know how to measure, then we tell you how to distribute the funds. Okay, in order to solve this problem, which is not trivial, that's why we wrote a paper about it. It's mathematical, but you can solve it, but it is not trivial. We had to make a mathematical model of the research activity. So in our model, we assume that there's a scientific community. There are units. Each unit can be a researcher, but it could be also a whole institute, right? I mean, I'm not saying anything about the scale of the units. Well, we postulate that this unit has something what we call a scientific productivity function. It's a function that relates the amount of funds that this guy is enjoying with the amount of science that he's producing. I mean, how do you quantify this? Well, you go to the evaluation part, okay? It's whatever objective measure that you decide to quantify science. Okay, so what is the goal of a funding agency? The goal of a funding agency, given some 4-year budget, is to find what is the best way to distribute it among all these units in such a way that the total output of the community is maximized. This is a simple problem. It's a problem of complex optimization, but of course it has a complication, namely that we do not know what these functions are. And I would imagine that they're difficult, if not impossible, to estimate, because you would imagine that these functions should change with time, and also would be probabilistic. So by the time that you can estimate something, probably the functions have already changed. So you can't really solve the problem by first estimating this and then solving the problem. It won't work. Now, how can you solve these kind of things? Well, you can apply scientific policies. You can apply some fixed rules to decide what is the fund allocation at each term, and it's every 4 years, and then hope that these rules are clever enough so that we would to steer the community to a situation of maximal productivity. Okay, I'm going to speak about 3 types of scientific policies. The first one is what I call the excellence policies. These are policies in which the amount of funds are increased with the production of the scientist or the research unit, and also with the previous funding that the research unit was enjoying. Now, this part seems to be very logical. This part is a bit illogical, right? I mean, why should you get more funding because in the past you got a lot of funding? Well, it's not logical to me either, but this is the kind of things that, for example, the European Research Council asks when you apply for a grant. They ask you to tell what is the amount of grants, what is the funding that you got in the past. And some people are very well thought, and they think, maybe they want to take into account how much money this guy had to produce these results, and then therefore he had a lot of money, maybe they won't give the money. No, I'm not an idiot, okay? What you see objectively is that people who got a lot of funding in the past, they get a lot of funding in the future, right? I mean, so, well, how can you model this mathematically? Well, a possible way would be the simple way. The amount of funding that this guy is receiving on the k+1 term is proportional to the output, the scientific output of this guy, measured by this objective measure that I don't want to talk about, multiplied by the funding that this guy was enjoying in the previous term. Now, how does this work? What would happen if we implemented this kind of science policy? You also have to go to the worst case scenario. The worst case scenario for an excellence policy is that all scientific units have more or less the same productivity function. So suppose that all of them have this productivity function, is some sort of geometric function that depends on the budget, like this. And then let's try to solve this optimization problem. What you find is that the optimal solution is to give each part the same amount of funding, and then you find that this is the optimal productivity of the community. Now, it could be that you don't know that all these parties have the same productivity function, right? In which case, you would apply some excellence policy. What would happen? If you apply an excellence policy in the limit of many grant calls, what will happen is that all the funding will be concentrated with just one individual. Which one? The one which had the greatest amount of money at the beginning of the call. Now, what will happen if you concentrate all this budget, capital X, into this one individual, will be that all the productivity will be given by this individual. It will be 8 times x to the power of alpha. So now you divide the scientific production that you will get with this policy divided by the optimal solution, and you find that in the limit when the number of the population turns to infinity, this goes to 0. So excellence policies are really, really bad, at least in situations where the community is very large. Now you could argue, well, you only prove this for this particular excellence policy. There could be others. You could take here the square root or something like that. It's true, but this holds for any excellence policy that tends to a configuration where the funding is in the hands of a constant number of units. You always have this problem. And now, I leave you thinking about ERC grants, okay? Think for 2 seconds, 1 second, okay, done. Okay, what else could you do? You could go all the way to the opposite side. You could say, okay, well, I'm going to give the same amount of funding to everybody, disregarding the ability of each unit to produce science. And then what you got? Well, the worst case scenario in this case is the scenario in which all scientific units except one are extremely inefficient, which could also happen, right? I mean, this scenario went to the extreme. They don't produce anything, and this guy produces something linear. Okay, in this case, the optimal solution is to give all the money to the unit that is actually working and none to the others, right? And then you get this production. But in the egalitarian policy, you get just 1/n, this production. Again, if you divide the production that you get in this scenario by the optimal solution, you find that the quotient tends to 0. So egalitarian policies are not a solution either. Now, is there any policy that works? There are several policies which work. And in this paper, I'm going to speak only one because I only have time for this one. We call it the rule of 3. And what I like about it is that an 11-year-old could have come up with this policy. The idea is like each party gets rewarded proportionally to the production that they had in the previous period. It's as simple as this. Now, what is the worst case scenario? The worst case scenario in this case is really weird. It's a population where you only have 2 units. And one unit has a more or less constant production. Depending on how much money you give it, it will produce more or less the same. And the other unit is linear. So what happens in this scenario is that the optimal solution would be to give this guy very little money, just barely the minimum, so that he achieves this number, and the rest to this other guy. In that case, okay, this guy receives more or less €0, this guy receives €1, 1 million euros, depending on the scale, and the total productivity will be 2, 1 plus 1, sorry. Now, what will happen with the rule of 3? If you apply it a lot of times, what will happen is the opposite. The configuration, the budget distribution will tend to a configuration which the first guy actually owns everything and the second one does not own anything. And then the total production will be 1. Then 1 divided by 2 is 1/2. Well, this is the worst case scenario. So what are the features of this rule of 3? Well, in the worst case scenario, you're at 50% of the optimal solution, which is really, really good. And in order to arrive at this worst case scenario, you have to really fine-tune the conditions a lot. And actually, in realistic scenarios, we also compute it, and it's of the order of 95%, 90%. The final distribution does not depend on the initial funding. It may be that one of the guys was getting a crazy amount of money, the other one was completely underfunded, right? It doesn't really matter. All these initial conditions are washed out in the limit of many calls. And actually, you don't have to go to many calls because the speed of convergence is very fast. And most importantly, it is the only policy that we found that you cannot cheat it by playing with publication times. In the paper, we describe some other policies in which this ratio is equal to 1, but you can cheat them if they're very easy to cheat. Okay, so I would like to speak very, very briefly about how this work was received. At the beginning, we thought that a lot of funding agencies will contact us to ask us questions about our research, but this never happened. So we started taking a proactive approach and started calling people, right? And it was very fun. We met with Gregor. We talked to also some people from other funding agencies, and the experience was, I think, in general positive. At least they listened. There was one experience that was very, very scary. So a guy from the European Commission got very excited about our work, and then immediately thought about the part that we didn't do, the evaluation. He wanted to use some sort of combination of H-index, number of citations, etc. That made us shit on our pants. And the reason is that the rule of 3 and all these other strategies that we have in the paper are very effective. So whatever you put is going to optimize it. And as long as you put something sensible, it's fine. But what happens if you put the wrong measure, the wrong objective function? Well, one decade ago or 2 decades ago, China decided that what they had to do in order to improve the science was to maximize the number of scientific papers. Well, they were lucky that our work was not already there, because if they had used the rule of 3, very soon they have found a pile of papers going from the Earth to the Moon, right? But you don't have any promise that any of these papers will have any interest. So in regards to this, I would like to conclude with some story from Greek mythology, very, very short. So the story says that Eos, the Greek goddess of dawn, fell in love with a mortal called Tithonus. And then she asked her father, Zeus, to make Tithonus immortal. So Zeus said yes. Unfortunately, Eos forgot to ask Zeus to make the Tithonus also eternally young. And what happened is that Tithonus started aging and aging. He lost his hair, he lost his teeth, he got all wrinkled, and at some point he could hardly move. And then Eos lost interest. So what is the moral? The moral is that you have to choose well your objective function. Thank you very much.
What do you mean by fast convergence? How many rounds do you actually need? Because we don't have that many rounds, especially for early career researchers. We have 1, 2, maybe 3.
The convergence is exponential for the rule of 3. It's really, really fast. I mean, we made some simulations with real data from the START grant, and we used the most stupid measure, the number of publications, and then we tried to apply it. Actually, it was very interesting for this grant. We took like 6 people at random, and we found that 4 of them should have remained postdocs. 1 of them should have gotten like 4 million, and another one 2 million. It was some really weird configuration, and already in the third call, well, you were really, really, really close to the optimal distribution.
Just one thing I missed. Did you put in an offset cost? I guess, for instance, the egalitarian distribution wouldn't work because there's a certain minimum you need to even have any productivity should be flat at the beginning. Did you simulate this in any of your?
No, we didn't. Actually, there's another source of nonlinearity, and that's why I think that this scheme shouldn't be applied to individual researchers, because otherwise it would be very likely that you could get ruined from one year to the other, right? I mean, maybe it should be applied to the level of institutes or maybe of very large groups.
Hi, I'm a social scientist, so I have to out myself. Still, I'm interested because your idea is still based on the rationale that it's coupled, that like your success is coupled to productivity somehow. And I'm wondering, why are you then afraid of tying it to objective measurements like citation index? Because to me, it's somehow a double bias. So both is based on productivity, it doesn't say anything on the quality or on the innovativeness of your research, for example. Also, if you base it on
no, you can do it, and then you end up maximizing the success that the scientists can have in the society, right? I mean, but that doesn't mean that you're promoting science or doing good science, right? I mean, it's a really delicate thing to choose the right objective function.
Okay, so if there are no more questions, then we thank our last speaker again.